mostly I'm going to talk about insulators today, which is, you know, a little bit not in the purpose of this meeting. But the good thing about insulators is that in between two insulators, it's a semi-metal. So that's how this is going to tie up with the meeting. I was going to talk about some new fermions. Basically, all the subject is all the talk is going to be about non-semorphic symmetries, and these can stabilize different types of topological behavior. But today I'm going to just talk about insulators, and tomorrow you'll hear something about semimetals. I haven't slept last night, so this might be very incoherent. So the people who have been basically the people who have been doing my non-semorphic work, because I don't do any more work, are these people. And the insulating part was primarily done by Aris and Zijun. Zijun found the material that I'm going to be talking about, and Aris basically figured out the whole theory, so it's not really my doing, it's these two guys. And tomorrow you'll hear about the non-semorphic semimetals that the other people here did. Now, these people have permanent jobs, so I'm not putting their pictures here, and that's that. So what I want to talk about today actually is just the first part of this talk, and show you that, you know, topological insulators, you know, they've just basically started, and there's much more to learn, and there's much more to discover in them than we have already. And I want to start by actually asking the question: how do we understand, you know, topological insulators, or how I understand topological insulators? And on the left-hand side is the quantum Hall effect, which is represented by the fact that it's a bulk insulator but an edge metal. So you've got this edge state which you can't remove, and wherever you put your Fermi level, you're going to hit something. You're either going to hit a metallic state in the bulk, but then if you go into the bulk gap, you're going to hit a metallic state on the edge, and that state cannot be removed. Even if you add impurities, you're just going to reconstruct the edge and move the edge a little bit inward. Now, I'm not going to be talking about these types of edge modes, which don't require any symmetry, like in the quantum Hall effect. I'm going to be talking about mostly the quantum spin Hall types of edge states, which require an extra symmetry. So if instead of a chiral edge mode, you have chiral and anti-chiral mode, so if I had another mode here, just like in the quantum spin Hall or topological insulators, then you need another symmetry to protect your edge, and that's of course the time reversal symmetry. But what really, how do we understand, if I don't want to do any complicated theory, how do I immediately tell you that there's a topological class? Well, the main restriction, the fundamental thing from a symmetry point of view that's required for a topological insulator to exist is basically the existence of two-dimensional representations at some high symmetry points. And this is how I think the easiest way that topological insulators have developed and are still being developed. So basically, if you look in, say, K1 and K2 are some momentum points in a Brillouin zone of the Fermi, in the Brillouin zone of the surface, and this can be either, you know, this is the surface Brillouin zone of the three-dimensional. This can be either of these 4 points. Now, time reversal symmetry requires that you have Kramer's doublets both here and here. So here, 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 here. And if you only know that's the only thing you need to know to pretty much immediately see that you can have two kinds of insulators. And the reason for that is that if you know that you have to have a twofold degeneracy here protected by some symmetry, and a twofold degeneracy here, or here, or here, but let's just draw these two, K1 and K2, then you can immediately see that there's two ways of connecting the bands on the surface. These are surface bands, so I'm just adopting a surface-centric perspective where the bulk is gapped, and I'm asking what metals can you have on the edge, on the surface. And basically the surface can be either trivial, these are bands of the surface. These are just kind of impurity bands of the surface where they connect, the Kramer's partners kind of go away, but they connect, two Kramer's partners connect between K1 and K2. They don't switch partners, but there's also, and this is the fundamental kind of insight of Kane and a lot of collaborators, that there's a case in which they can switch partners. And the switching of the partners is still fundamentally stabilized by the fact that you have this Kramer's degeneracy here. But once you know that you have a twofold degeneracy on the that's respected by the edge or by the surface, you know that you can have these two types of flow. And this is non-trivial and this is trivial. Now, doing the same type of arguments, you can realize that there's many more topological insulators just by counting degeneracies. So for example, if I have a system with C4 plus time reversal symmetry, let's just think about a system with C4 plus time reversal symmetry, but now time reversal is spinless. So if I just have spinless time reversal, then there's no Kramer's theorem. So with spinless time reversal, I don't need to have double degeneracy, right? So this would be for bosons, for spin 1 particles or integer spin. But now if I also have C4, since I know the C4 squares to 1 in a spinless system, I know that the representation I, the eigenvalues I and minus I of C4 are related to each other by the spinless time reversal. The spinless time reversal is just complex conjugation, so it relates the eigenvalue I to the eigenvalue minus I. So I know that I can have a double degeneracy, and where can I have it? Well, I can only have it at points which are left invariant by C4 times time reversal. So for example, this point is left invariant by C4 in time reversal, right, because it's the gamma point, and this point is left invariant by C4 in time reversal because it's pi pi, right? This point is not left invariant by C4 in time reversal because it moves here and time reversal moves it here. But at least here and here with C4 and time reversal, for representations of bands that have eigenvalue I and minus I, have a twofold degeneracy. And that's the only thing that you need to know to realize that there's a C4 plus time reversal invariant class of insulators, because I can connect bands, I can switch partners of, they're not Kramer's partners anymore, but they're partners in this new symmetry group. I can switch partners between here and here, and this is, for example, a simple insulator that realizes that. So the moral of the story is, when can I have a topological insulator? When at least 2 points in the Brion zone of the surface, I have a more than one-fold irreducible representation. So for example, these two degenerate states are a two-dimensional irreducible representation. And the reason for that, as I said, is that once you have a twofold irreducible representation at 2 different points, you can connect the bands either by, in a trivial way, by creating impurity surface states, which are trivial, or you can connect them in this weird quantum spin Hall-ish way. So this was actually known for, I guess, years. But the question now is there something more? And so is there something more than just this criterion? And the answer is yes. This criterion just focuses on the surface. So now I'm just going to be talking about the surface still. Focuses on having double degeneracies, or more than double degeneracies, but at least double degeneracies, twofold degeneracies, at some points in the Brion zone. But there is an enhanced criterion for topological behavior, which focuses not only on degeneracies at high symmetry points, but on the way bands on connectivity on high symmetry lines. So what you need to add to this to this characterization of topological insulators, topological insulator behavior at points, you now need to add high symmetry lines. And I'm not sure that this is the end of it, but at least it's a generalization. So let me tell you what the criterion is, and then give you an example. So the criterion is the following: that you're going to have two submanifolds. So here a point was a submanifold, but here I'm going to be talking about submanifolds as high symmetry lines rather than high symmetry points. Two submanifolds of the surface Brion zone, S1 and S2, with connectivity D1 and D2, which are equal. And I'll explain what this means. But basically, I'm just going to put it here. I have two manifolds, S1 and S2. And these are high symmetry lines in the Brillouin zone with connectivity D1 equals connectivity D2. And there will be a submanifold S3, which is also a high symmetry line with connectivity D3, which divides D1 and D2. If this happens, then you can have a non-trivial topological insulator. So I'm going to go through that. This is kind of, this is not very explicit, but I'm going to go through that. But I guess the point here is that a lot of credit should be given not in terms of topological insulators, but for understanding this connectivity behavior and, in fact, its relationship to Wyckoff positions to Zach, who is now at the Technion in Israel. These are a series of remarkable papers that he wrote, I think, in the 90s, early 90s, that, I'm just going through them and just finding more and more things to look at. So, okay, so let's understand this criterion. So now I'm going to show you a material, and I'm going to show you this, what I mean by connectivities, and then I'm going to explain why, the connectivities are what they are. So this is the surface Brillouin zone of the 0, 1, 0 phase of this material, which is mercury, potassium, and X can be antimony, arsenic, or bismuth. Okay? Unfortunately, I know only 3 materials that have this behavior, but I'm sure there's more. So if you look at this material, you cut the surface, it's not a natural cleave plane, but as I'll show you in the experiment that's been performed, you can do it. If you cut on this surface, the surface Brillouin zone is going to have the following high symmetry lines. This is a high symmetry line, this is a high symmetry line, this and this. Now these lines differ by the symmetries that they respect. For example, you can think of this as this kz. You can think of this is kx equals to 0 and kx equals to pi psi symmetry lines, well, half of them really. And what they actually are invariant under is a mirror symmetry. X goes to minus x. You can see this mirror symmetry, x goes to minus x, which takes mercury into the X atom. But then you can translate by half of the unit cell. And this is a noncemorphic symmetry. So you can x to minus x and translate by half a unit cell. So both these surface planes are invariant under this symmetry. And I'll show you that this symmetry immediately gives you a connectivity of 4. So these ones, D1 and D2, is equal to 4 in the sense that on these two high symmetry lines, you cannot have less than 4 bands. And you cannot have bands that come in multiples. You cannot have 6 bands. The bands come in multiples of 4 on these lines. And they have to come in multiples of 4 due to this noncemorphic symmetry. Now, notice that this is not what you'd expect if you just looked at these high symmetry points. If I just looked at the previous criterion of looking at high symmetry points in the Brillouin zone at 0 and y, or whatever you want to call the z, in the Brillouin zone of the surface of the material, here I would have time reversal, okay? And time reversal plus some other symmetry would still enforce just twofold degeneracy. So if I just look at these points, you can see here and here, I just have twofold degeneracies at these points. So I would think, that nothing different can happen from the usual case of the normal topological insulator of K and Meli. But if I look on the high symmetry line, I can, and I'll show you why, I can immediately see that instead of just having twofold degeneracies at these points, these twofold degeneracies have to be connected in a very weird way, which we're going to call hourglass from now. I guess in Europe there is called a sand clock? No? That's how it's called. Yeah, okay. In the US, I think it's called an hourglass. Anyways, it's a yeah. So now, so these are the two manifolds, S1 and S2. These are these high symmetry lines. And now notice that there's another manifold, which is the red one, where bands come in doubly degenerate. And I'll explain why they come in doubly degenerate. this is twofold degeneracy. And the criterion says that this has to divide this, and it does. And if this divides this, then I can draw the following surface band structure. Just look at this side of the surface, just this a triangle. This is another. This can vary. I can have more than one choice here. But the point is, all of these, irrespective of what's happening here, this is a non-trivial insulator because you can see you cannot connect it within itself. You have to connect it up in the bulk. So this is the band structure of the surface, and somehow something has to get connected to the bulk. You can't just draw bands that remain connected only by using the surface. You have to use the bulk too. So if we do this on the surface of this material, what you get is the following thing. This looks very much like this is Z gamma here. This is Z gamma here. And you can see that you have something that looks, of course, the details are a bit different. This is a squashed hourglass, but it looks very much like this one. Now, here, you can see that the bands, I can see only 2 bands here and here, but there's 4 bands coming out of here at this point. So you know that these bands have to be doubly degenerate, and this is what the ab initio gives you. Moreover, if I actually took this code and put in another surface potential, where I didn't put it, but Zijun did, if we did that, you could raise this hourglass, you could make this hourglass go up into the bulk, but then you'll bring in another hourglass on this high symmetry line here, okay, which is this one. So basically the moral of the story is that this material has this type of surface state, which is very much different from, you know, the usual Dirac fermion, which looks like this, on either this high symmetry line or this high symmetry line. Okay. In passing, I want to mention how this relates to semimetals. So the way we started thinking about this material, well, really the way we started thinking about this material is that we are looking at some older paper of Claudia Felser and Bingheiss, where they were looking at materials which had topological insulator behavior, meaning time reversal topological insulators. And then what we noticed basically is that in this material, if you just try to build a molecule of the material without you know, just this unit cell molecule, what you find out is that this mercury goes below the antimony, and this is actually not this is actually not normal. Why? Because mercury here is, I guess, 6, right? So 6 and antimony is 5, 6s2 and 5p something, right? So normally this should go above, but there's something in chemistry that I learned by visiting Claudia that's called the inert pairing effect that makes this go below this, okay? And once this has gone below this is non-trivial, and you know it's non-trivial without doing any more work. The reason why you know it's non-trivial is that without adding any spin-orbit coupling, this guy is a semimetal. Okay? It's very much like graphene. Remember when Kane and Melly did the graphene model? The way they did it is they looked at the graphene model without spin-orbit coupling. Now, without spin-orbit coupling, it's a metal. It's got these, you know, Dirac nodes graphene. But graphene is already inverted without spin-orbit coupling, meaning that whatever small amount of spin-orbit coupling you add in graphene, it's going to go topological. It's got no other choice. The reason for that is that graphene, if you take the product of the inversion eigenvalues, you know, graphene is gapless at points which are not inversion symmetric. I mean, they're not, you know, they don't go under themselves. They switch. This K goes to K prime under inversion. So graphene is actually gapped at all inversion symmetric points. So you take the product of the inversion eigenvalues of graphene below, you know, of the bands below 0, and you get -1. And that tells you that immediately graphene is inverted as a metal. So it tells you that if you open a gap, any gap you open, you get a quantum spin Hall. And indeed, there was, you know, I mean, you know, if there were, in the original paper, I think they made this point that, you know, no matter what spin orbit coupling you add, graphene will be a topological insulator. Same thing with this guy. Because this, without adding spin orbit coupling, if you look at mercury and antimony, you'll see that the Fermi level slashes through the antimony orbitals, and it's fixed to be here. And when you add spin orbit coupling, the only way that the levels can go is as I showed them here. And if you actually compute another inversion quantum number, it's not an inversion symmetry quantum number, but it's inversion of some screw rotational eigenvalues, which is this, this material has a screw axis which you rotate by 60 degrees and translate by half a unit cell. By 30 degrees and translate by half a unit cell. And you can compute those rotational eigenvalues and do the same thing as you did in graphene, take their product, and you find out that it's inverted. And that basically tells you that this material will do something non-trivial once you add spin orbit coupling. Now, it doesn't tell you the full story, but it tells you that there's something non-trivial. Okay, so to understand all these connectivities, I need to introduce this concept of noncemorphicity, and many people know it, but I just thought for completeness I introduce it. And the concept of noncemorphicity is a concept that basically lets you draw lattices in however many dimensions you want. So I want to basically take the following object and draw something that's periodic in space with this object. Now there's one immediate way of doing it, which is just repeat it, right? And this is called, this is called a symorphic representation of this symmetry. This object has the symmetry that if I take x to minus x, it remains the same. Now, what I'm doing here in mathematical terms is extending this symmetry by translations. So I'm trying to take a symmetry that's Z2 symmetry. It's just taken identity and mirror squared is equal to identity, and trying to extend this group by translations. There's an easy way to do it, which is this one, which is obvious. But there's a less obvious way to do it, which is this one, which you just take this one, move it by half a unit cell, and then translate it. Now, these are the only two ways of doing such a thing, and I'll come back to it later. But the moral of the story is that, for example, you're never going to find crystals where you can translate things, where you have mirror symmetry and translate things by a third of the unit cell. It's always a half of the unit cell, and there's a mathematical reason for that. So the point is, these two types of situations are symorphic and non-symorphic, or for group cohomologists, this is trivial, the split representation, this is the non-trivial extension. But all you're doing is you're trying to extend your symmetry group by the group of translations. Now, this one is the one that we'll be focusing on, because as I said, we have this symmetry that if I look at the face 0, 1, 0, and I take mercury into, and I apply a mirror, I take mercury into antimony, so I have to translate by half a unit cell, which is exactly what I'm doing here. Let me show you how this changes things. So here I'm looking at the surface 0, 1, 0. Of course, Kz is coming out of the plane. Out of the plane, you can see it. This Kz is kind of, right? And you can clearly see that if I make a mirror symmetry x to minus x, or just make this mirror symmetry, then this is not a symmetry unless I translate by half of the unit cell out. So let's try to implement that symmetry on a lattice. Well, it's pretty clear that if I make the symmetry and translate by half unit cell, if I do the same thing twice, I translate by 1 unit cell. So what that means is that if I square mx, I've translated by 1 unit cell, and I represent that by a phase in the block representation, right? That's just e to the I k z, because I've translated by 1 unit cell in the z direction. This minus here comes because I'm looking at spinful groups, so I'm actually also rotating the spin, right? So this is why I get 1 minus when I do mirror squared, but this phase is the non-symorphic phase. This phase is what will cause all the interesting, well, hopefully interesting things. So if I have mx squared is equal to minus from the spin exponential to ikz, which is which is from the non-semorphic nature of the lattice, then I have two branches of eigenvalues, plus or minus I times the exponential of I kz over 2. You can clearly see them from here. Now I'm going to call the dotted one the minus, and the full line the plus eigenvalue. And this plus or minus just refer to these two plus or minus. I think these were Lucas's talk this morning basically presented this also. The moral of the story here is that if I now have this symmetry group but also time reversal, you can see that time reversal does very different things at kz equals to 0 and kz equals to pi. So I'm looking at the behavior of bands along either this line or this line. At kz equals to 0, the eigenvalues of mx are imaginary. So this is kz equals to 0, are imaginary, right? So this is minus I, this is plus I. If they're imaginary, it means that time reversal flips them, because time reversal is just complex conjugation plus a spin factor, but it doesn't matter. Time reversal acts by taking I to minus I. So it means that the Kramer's degeneracies at kz equals to 0 come between dotted and solid. But at kz equals to pi, you can now see that exponential to I pi over 2 is imaginary. So these are either 1 or minus 1, plus or minus, right, the eigenvalues. Well, the minus 1 is minus I times I, which is plus 1, okay? And this one is minus 1, okay? So at kz equals to pi, time reversal, which is complex conjugation, cannot take this into this, right? Because complex conjugation of 1 gives you 1. So what time reversal does at kz equals to pi, you still need to have Kramer's degeneracy. What time reversal does is it makes two bands, okay, of the same type, either dotted or non-dotted, link in a Kramer's doublet. This is a Kramer's doublet. And at kz equals to 0, the bands have to do this. Okay? So given those two restrictions, which you can clearly see them here and here, here and here, there's only two ways of linking the bands. Okay? One way of linking the bands is this way, which has a flow. This is just the surface, right? This is the Brion zone of the first surface. This is a weird flow. This is just the quantum spin Hall flow, really. If I didn't tell you that this was dotted and this was not dotted, this would just be the Kane-Melli quantum spin Hall flow. You can call it the glide spin Hall effect, because you can actually measure glide eigenvalues in ARPES, turns out. But the interesting flow that I want to talk about today is this hourglass flow. You can immediately see that if I impose this constraint at kz equals to 0 and this constraint at kz equals to pi, which just comes out of this non-semorphic symmetry plus time reversal, I can immediately have this flow, and this crossing will not gap because it's a crossing between two different non-semorphic eigenvalues. And this is the hourglass flow. Now you immediately see that with this symmetry you cannot have bands that come not in multiple of 4, right? The connectivity of these bands is 4. And this degeneracy here is movable, so it shows up on this high symmetry line somewhere, but non-removable. I can't gap it. I can move it around, but I can't remove it. Now, and that's why this connectivity is 4 on this manifold. Now, on this manifold here, which is the kz equals to pi manifold, that's the kz equals to pi manifold, okay, as a function of kx. You can immediately see that I have another symmetry. So mx takes kx to minus kx, but time reversal takes, again, kx to minus kx. It leaves this invariant, because minus pi is pi. So then I have the symmetry t times mx, which takes kx into kx. So this is a good symmetry at each point on this manifold. But this symmetry is also special because of the non-semorphic nature of the group. And the way to see that is to just square it. So normally, if I square time reversal times any spatial operator, time reversal has to commute with spatial operators. So this is t squared times mx squared. And normally t squared is -1 because I have spin. And mx squared is, if I have a symmetric group, I'm just rotating the spin, so I get -1. But my group now is non-symmetric, so I get -1 e to the I kz, just as before. And at k is equals to pi, this is 1. So instead of this giving me 1, it now gives me -1. And this is a fundamental thing, because I can now call t times mx a new operator, t tilde, which acts like a time reversal anywhere in these points, right? It acts like a spinful time reversal. It contains complex conjugation because it borrows it from this time reversal, and it squares to -1. So it acts like spinful time reversal. And spinful time reversal has Kramer's degeneracy, but unlike time reversal, this acts at every point on this line, so bands are doubly degenerate on this line. So this is the connectivity d3 is equal to 2. So if we patch them together, I can get several things. I can get, I can patch these together in this way, which is the trivial way. I don't want to patch it together in this way. I can, why is this trivial? Well, this is the Briand zone of the surface, and if bands can connect, the moral of the story is, can bands connect themselves on the surface without needing the bulk? And this, in this case, they can. In this particular, this is kind of like the trivial insulator case. But the non-trivial insulator case, which is this one, also has to exist. Okay? And it exists in this material. Now, we can talk about what's happening on this line here. On this line, there's yet another symmetry, but I need to introduce another mirror symmetry, and this is not really that important. The moral of the story was all about these different manifolds. This is S1, S2, and this is S3. And the fact that if I have different connectivities in the middle, in the manifold connecting these two, I can have a topological non-trivial insulator. How much more time do I have?
As long as you want. Half an hour.
Half an hour, okay. Okay, so now let me show you some ARPAS data of this on this material. So, okay, so the moral of the story is, well, one of the moral of the story is, in ab initio, this hourglass is very, very squashed. You can clearly see it here. So, initial ARPAS data will probably not see all the 4 branches, but you can expect them to see something that looks like this here. Now, this is a double degenerate line, as I said, because this connectivity is 2, and I've explained why. This is connectivity 4, and it turns out that on this side, which is the only one we haven't yet explained, but this is not important, the bands are singly degenerate, and you can see them 1, 2, and if I had higher resolution, 3, 4, or you can see them clearly here with another surface potential. These two figures just differ by a surface potential. This is the realistic calculation, but the point is the degeneracies of these bands here are singly degenerate. Here it's twofold degenerate, and I have an hourglass in between. So ARPAS shows this. Okay. So this is the, well, supposedly this is the dots here. Supposedly, like the lines here are experimental data. Okay. Like these bold lines. Okay. So yeah. Okay. But the point is, these are the lines where you should have a twofold degeneracy. Okay. These are the points in the Briand zone where you should have a twofold degeneracy, and you see just so you have 4 bands, each twofold degenerate, and you can just see the 2 peaks. Here are the lines where you have the singly degenerate bands, and they claim that this, you can see different types of peaks. There's 1, 2, 3, 4. Now here, this is the hourglass here. You can see that they can't distinguish it, right? So the hourglass should actually look like, the hourglass should actually look like this, okay, and on the other side is, of course, the time reversal of this. With this one being very close to the edge. And they cannot resolve this difference. They can just resolve this. And this is what it's claimed to be here, this and this. Now, of course, you know, you can, you know, it's in the eye of the beholder. But the point is there is something in the gap of this material. This is very clear that there is something in the gap of the material. And if you've got a loving eye, you can actually try to convince yourself that it matches the theoretical prediction quite robustly, with the exception of the hourglass, which is quite squashed. So that's why you can't see all the 4 bands. You just see this and this. Because of a weird you know, plotting technique that they had, this is actually, you should just swap this, right? This and this are this and this. Okay. So I'm going to, this is, you know, this was the less mathematical part of the talk. So I'm going to like explain what I'm going to explain what's interesting about. I mean, you know, this looks messy, but in a way, like, you know, Zach could have done all this, I don't know, 20 years ago, because it's really just counting eigenvalues and following them as they go through the Brillouin zone, and realizing that, you know, there's some situations where you need a bulk. You can't just continue the flow on the edge, just like Kane and Melly did. Now, what I've argued is that on these lines where I have, on these 2 lines where I have mirror x, which takes, this is kx, takes kx to minus kx. Okay, so it leaves these lines invariant. Okay, but mirror x squared is equal to minus e to the I kz, and this is z, kz. I've argued that you can have 2 types of flows. So one flow is the hourglass. Okay. Okay. And the other one was the quantum spin Hall, which I said, you know, which I said is something that's, sorry, that's like this, right? The only constraints are that kz equals to 0, dotted, this is kz. At kz equals to 0, dotted and solid come together in Kramers because their eigenvalues are plus I and minus I. And at kz equals to pi, solid and solid, or dotted and dotted, form Kramers pairs because their eigenvalues are 1, as the eigenvalues of the mirror change as I move kz. So I can have 2 different types of flow. Okay, I could have this flow if I wanted to. Okay. Right. So this is a quantum spin Hall flow. This is, as I said, Kane and Melly, but with just where bands have some mirror eigenvalue. So the moral of the story is that by just looking at the surface, the symmetries of the surface tell me that I can have an hourglass here, or a quantum spin Hall here, and a quantum spin Hall here. So I could have all of these flows here. Now, in the material that we had, I had an hourglass here and here, but in principle, just from what I've told you now, I could find materials where I could have the quantum spin Hall here and quantum spin Hall here, another type of insulator. What I'm going to argue now is that the quantum spin Hall here cannot happen. It can happen only here. And this is actually a major difference between looking at the surface and looking at the bulk. Most people, well, not most people, but most research so far has focused on finding the symmetry group of the surface, and then, you know, like time reversal, for example, and then seeing how bands can connect on the surface. Okay. But it turns out that that's not the whole story. So the next, I don't know, 15 minutes are going to be to explain why on the K, this is This is kx. On the kx equals to pi plane, which if I was looking at the surface, pi goes into minus pi if I apply mirror, but minus pi is equal to pi on the surface, so this would be a high symmetry plane under mirror, mx. Okay? Why on this plane here, you cannot have the quantum spin Hall, you cannot have the quantum spin Hall flow, you cannot have this, whereas here you can. So basically this is kind of, I don't know, when Aris first found this, I found it kind of amazing because you've got two planes which on the surface look the same under mirror. The kx equals to 0 under mirror, x goes into kx equals 0. Kx equals minus pi on the surface goes into minus pi. With kx equals pi goes into minus pi, which is equal to pi. But one of them, so on the surface they look the same, but they're actually very, very different. And the way to see this is to actually look at the material in the bulk. So now I'm not going to go to the surface, I'm going to be done with the surface and try to obtain the topological invariance of the material from the bulk. So far I just looked at the 0, 1, 0 surface, and I just looked at the symmetry group and just analyzed bands. But now I don't want to look at the surface anymore. And I will argue that the bulk tells me something that the surface hasn't. So to start off, I'd like to introduce the concept of Wilson loops. So Wilson loops, the reason why they're interesting is that they allow you to look at the surface without actually cutting the material. So Wilson loops are basically something that everybody in ab initio who wants to compute topological invariance has to do, because they're not computing Chern numbers and Z2 invariance the way, for example, the way Kane and Melly found the Z2 invariance with the Pfaffian is very nice theoretically, but practically it's not very useful because you need to fix a smooth gauge, and that's almost impossible, or it takes a very long time. So Wilson loop is the way you actually do it in any real material. So what happens is that I have a set of bands in a material. This is bulk bands with a gap, however many bands with a gap. And if my Fermi level is here, what I can do is I can just build a projector at each k point into all the occupied bands. So this is all sum over n occupied of psi n, and this is at each k point. The Hamiltonian is diagonal in k, in momentum space, so I can always build this projector. Now once I build this projector, I can do weird things with it, such as do parallel transport. So the reason why projectors are good is that you start with an eigenstate at some momentum k. Notice that the bands are orthonormal only at the same momentum. So for example, psi n of k, psi m of k is equal to delta mn, but there's no such relationship between psi n of k and psi m of k prime. This is not equal to delta mn if k prime is not equal to k. And the reason for that is that you just start with an eigenstate of momentum k, and the way to actually smoothly transport it in the Briand zone to another momentum is just to add a bunch of projectors. When you do that along a path, all you've done is to make a Wilson loop. Now, this Wilson loop actually has a very nice expression. It's just the integral of the non-abelian Berry curvature, Berry potential, along the loop that you're taking. And here, what I'm taking is a loop in my material that's along ky. So it starts at ky equals to 0, and it goes all the way to ky is equals to 2 pi. So I start with an eigenstate at ky equals to 0. Okay, so I start with psi at 0, and then I hit it with a bunch of these projectors. I hit it with a projector at the immediate momentum, 2 pi over ny, where ny is the number of sites, and I hit it with a projector at 4 pi over ny, and then I hit it enough that I get to the eigenstate at 2 pi, at ky equals 2 pi, which is up to a unitary, the same as the eigenstate at 0. And this is this quantity. This is the Wilson loop, and you can index it by a direction, which is direction which I'm going. And the reason why I'm doing it in y is because the surface that I wanted to look at in my material is perpendicular to y. So the moral of the story is that if you want to find out what the surfaces do in materials but don't want to actually cut and calculate band structures with surfaces, the alternate route is to just look at the Wilson loops in the bulk of the system perpendicular to the surface. So you ask, I want to know what my edge modes do on the 0, 1, 0 surface. And what you do is you take your Wilson loop at ky equals to 0, which is perpendicular to the 0, 1, 0 surface. You continue it, you do this, you started at ky equals 0, you continue it up to ky equals to 2 pi. Okay? Now, if I do that, notice that this is the 0, 1, 0 surface. I'm drawing a square Brillouin zone just for kicks. Okay? I just take this Wilson loop at ky equals to 0. This is ky. I continue it up to ky equals to 2 pi. This Wilson loop has a momentum which is kx, kz. So this is identified by kx and kz. So all that I'm doing is I'm taking an eigenstate at some momentum kx, ky, kz, and ky equals to 0, and I'm continuing, keeping the kx and kz constant. I'm just hitting it with the projector up to ky equals 2 pi. The reason why that I don't have time to go through it, but the reason why that's interesting is that actually gives you the spectrum of the surface state. And moreover, notice that you don't need to gauge fix, because these projectors, if I write them like this, are gauge invariant. So whatever gauge you have in your computer, whatever your computer spits out in ab initio, you can do this without any further help. So, for example, let me show you what happens when you have a system like a Chern insulator. So say I have a Chern insulator, which is a quantum Hall effect, and it's supposed to have an edge state. Right? So if I have a Chern insulator and compute the Wilson loop, what will happen is it's a two-dimensional system. Right? Chern insulator is just quantum Hall. Two-dimensional systems. This is, say, ky, kx. I compute the Wilson loop. I take it from here, take the eigenstate here, project here. Okay? This is the Wilson loop at some kx. I look at its eigenvalues. It's a unitary matrix. Its eigenvalues are between 0 and 2 pi. And I look at how its eigenvalues vary as a function of kx. And the way they vary as a function of kx is that they wind around if the system has a Hall conductance of 1. If the system had a Hall conductance of 2, they would wind twice. So you can immediately tell you the Hall conductance. Now, how about a quantum spin Hall case? Quantum spin Hall. So if I have quantum spin Hall, I do the same, but now I know that if I have a quantum spin Hall, the occupied bands come in Kramer's pairs. So my Wilson loop is a 2 by 2 matrix. I have 2 eigenvalues. And I just look at what they do as a function of kx. Think of this as kx. But now only between 0 and pi, because I have time reversal. I'm not looking between 0 and 2 pi in kx. I'm looking what they do between 0 and pi. And notice this is the non-trivial. This is just the Kane and Melly model. You can see that they wind. They wind in like a very symmetric way. And this is the trivial case where they don't wind. So the moral of the story is that Wilson loops tell you your edge behavior without actually putting an edge in the system. So you might wonder why this is just the time of this is just Kane and Melly model, or actually it's just mercury telluride, but whatever, same thing. So you might wonder why are they degenerate here and degenerate here. I remind you that minus 0.5 is equal to 0.5 because the eigenvalues, these are the eigenvalues of the Wilson loop, are 2 pi periodic. The reason why they're degenerate here and here is that time reversal also applies on the Wilson loop. So just like it applies on the Hamiltonian, the symmetries of the system are already included in the Wilson loop. So here you got a Kramer's degeneracy in the Wilson loop. Here you got a Kramer's degeneracy in Wilson loop. Okay? So this is exactly like a neater way of just doing the edge spectrum. But the moral of the story is that if I have a symmetry G on the Wilson loop, this symmetry G can leave my Wilson loop invariant or change it into minus itself. Okay? For example, if I had a Wilson loop whatever. If I had, the point is there's an action of the symmetry on the Wilson loop. So if I had this Wilson loop here at kx equals to pi, okay, or kx equals to 0, and this ky, so I took the Wilson loop here, mirror symmetry would leave my Wilson loop invariant, because mirror x, because it would not change kx. Right? So if I took this Wilson loop like this, mirror x would leave it invariant. But time reversal would flip it, right? Because it changes. Time reversal flips the momentum to minus itself. Okay? The moral of the story is that whatever symmetry I've got G, when it acts on the Wilson loop, it gives me the Wilson loop to plus or minus 1. And that means that I have a Wilson group. So now I can define a Wilson group where instead of just looking at the Briand zone or at the symmetries of the system plus translation, I'm trying to extend my symmetry by the Wilson, by the way the group acts on the Wilson line. This is very similar to how I looked, say, at noncemorphic things. Remember how I built the lattices? I was trying to look at noncemorphic things and then I was trying to look at mirror and then enhance mirror by translation. And I found two different ways of doing it. Well, I didn't find them, but mathematicians found them in the past, two different ways of doing it. That's the same thing that we're doing here. We're trying to enhance the group that we had by Wilson loops. Now, why is that interesting? Well, first of all, just as I said, all that we're doing is we're now trying to just enhance the symmetry that we already had, which could be symorphic or non-symorphic, by another Wilson group. So these are the two ways of enhancing this. This is a repeat slide. This is just the two ways of enhancing this the mirror squared by translations in real space. Okay, and just as an aside, you can actually compute how many ways you can enhance mirror by translation, and that's just given by the second cohomology group. So in any case, that's just the math talk. But basically, the second cohomology group of mirror extended by translations. Translations are just a Z group. Why? Because translations are just 1, 2, 3, 4, 5. They're isomorphic to Z. This is Z2, and this just tells you that there's only two ways of extending mirror by real space translations. And that's what we found. One of them is the symorphic way, the other one is the non-symorphic way. And that's actually how you come up with the whole description of groups, just by computing cohomology. Okay? So now, what I'm going to try to do is extend my symmetry by this Wilson group, by this new Wilson group. Now, notice that this is a momentum space, right? This is a momentum space. The Wilson loop is dependent on the momentum. So basically what, in a more kind of like, metaphorical sense, what we're trying to do here is implement non-symorphicity in momentum space. So we had non-symorphicity. Notice that up to now, non-symorphicity is just in real space. So you kind of just you make your mirror symmetry and you translate by lattice translate by half a lattice half a unit cell. Okay, but your Hamiltonian was still diagonal in K. So non-symorphicity up to now was kind of one-sided on the real in real space. This will extend it to momentum space. I'm just going to take like 5 more minutes because this right. What time is it? Not being very forceful. Okay, you should be more forceful. Just turn the laptop off. Okay, okay. This is going to be done. So the point is here. If I look at the primitive Briand zone of this material, of this potassium mercury telluride. And this is the fundamental thing that shows you that there's a new type of symmetry. You look at the primitive unit cell of this, and you look at kx equals to pi. Remember, I was trying to argue that something is different between kx equals to pi, that here you cannot have quantum spin Hall, and here you can. So I was trying to argue that something is different from here to here. What's different? Look at the primitive unit cell. This is kx equals to pi. Okay, the Wilson loop is already taken. Okay, is taken as a function of ky here. Okay, so I'm taking the Wilson loop dot projecting here, and I'm going to apply mirror symmetry. If I apply mirror symmetry on kx equals to 0, nothing happens. If I apply mirror symmetry on kx equals to pi, I switch it to kx equals to minus pi here. Okay, I'm going to go from kx equals to pi to kx equals to minus pi. But in this material, the primitive unit cell doesn't have a translation by a vector that's perpendicular to the kx equals to pi plane. So in other words, the kx equals to pi plane goes into kx equals minus pi, but this gets translated by a vector which is b2, which is not perpendicular to the mirror plane. So in effect, when you're starting with a Wilson loop here, after you translated it, you end up with a Wilson loop that starts here. Okay? What that means is the following, that these two planes are inequivalent. So what that means is that if I look at the kx equals to 0 plane, okay, and I perform a mirror symmetry, nothing happens to the Wilson loop. So the mirror symmetry still squares to minus a unit translation, which is just e to the I kz if I represent it in momentum space. However, here in the kx equals to pi, if I take the kx equals to pi plane, I make a mirror transformation to kx equals to minus pi. My vector b2, which is the reciprocal unit vector, doesn't translate me back to the same point. It shifts me up. Okay? And because it shifts me up, I cannot write something that looks like mirror x Wilson loop mirror x to the minus 1 is equal to Wilson loop plus or minus 1. I can't do this because these Wilson loops, once this one was started here, when I go here by mirror, when I translate here, this starting point has been translated. Okay? So it would seem that this plane does not have a Wilson group, but that's wrong. You can actually extend the mirror symmetry. You can build a new mirror operator, call it mirror tilde, which is the old mirror operator times a Wilson line. The Wilson line is just a line that goes in for half of the Briand zone, for half of this high symmetry axis, and you can form a new group with that. But that new group is going to have a different group structure. So at kx equals to 0, the group structure is that mirror squares to just the translation by a unit cell. This is just, the noncemorphic normal thing. But the kx equals to pi mirror squares to translation by a unit cell times a Wilson loop. Okay? And you can kind of clearly see that this is just an extension of this group. Now, I could go through this, but the point is that this type of group structure that's different here from here at kx equals pi, kx equals 0, actually forbids such a glide spin Hall effect on this line. So this line in this material can only have an hourglass. So only hourglass in this. So this is not very experimentally relevant so far. Well, it's really experimentally relevant if somebody finds an hourglass quantum spin Hall here, because then it would mean this whole theory is wrong. But I doubt that that's going to happen. So the moral of the story is that there's materials where you can have hourglass fermions on some high symmetry lines. You can have connectivity larger than 2, even though at high symmetry points you still just have Kramer's degeneracy, but in between them they connect differently. And that if you just look at the surface, two planes such as kx equals to 0 and kx equals to pi can look very similar, but if you look at the bulk, their actual group structure is completely different, and you need to extend the group at kx equals to pi by a kind of a noncemorphic momentum translation, just as you extended the group of normal symmetries by lattice translation. So this kind of puts lattice, the real space and momentum space on the same footing. So that's the end of it. So I think I only went 3 minutes overboard. So thank you so much.